Thanks for joining us this morning. So I will speak about simulating star formation, and well, it is really a broad topic to cover. So I'm trying to give an overview, and of course, happy to discuss more details if you have specific questions. Right. So then I hope that this works now. No. I need to click here. Okay, so I usually don't do these outlines, but in this case, I thought it is worth it because it is a very broad topic. So we first give a brief introduction, what we need for star formation, so basically setting the stage. And there will be many lectures about larger scale interstellar gas. And therefore, I decided to start on the scale of prestellar cores. In this lecture, we will only briefly touch upon larger scales when we speak about feedback, but it's really mostly about prestellar cores, meaning that we are definitely below 1 parsec, and typically the scales of prestellar cores are like 0.1 parsec, something like this. So then we will also speak a little bit about disks, because disks are a very important aspect of the star formation process, and about multiplicity and initial mass function. So this will be just setting the stage, what we aim to model with our star formation simulations. And then we will see how fragmentation proceeds in these prestellar cores. We will speak about physical processes which are involved and how to model star formation then with numerical simulations, and the impact of initial conditions, and then also stellar feedback, and how to finally get the stellar initial mass function out of the simulations, or actually we will see whether we are there yet or not. Okay, so let's start with the introduction. So, I mean, probably you all know that stars form in cold and dense molecular clouds. And this is one of our favorite molecular clouds, the Orion Nebula, which is the nearest massive star-forming region in the galaxy. It's just like about 1,500 light years away, and it has a mass of several thousand solar masses going into stars. So it's really a star factory, and in particular, it's also forming massive stars. So it's not like other nearby molecular clouds in the gold belt, which are mostly low mass star forming regions. Here we also form massive stars, and you can beautifully see the effect of massive stars on the cloud because of this bubble which is blown into the cloud, you know, starting from the trapezium cluster, which is the cluster of massive stars, which is sitting here. So this is a Hubble image, so it's really visible light. And however, as we know, the interstellar extinction scales with the wavelength. And so therefore, if you go to longer wavelengths, your extinction will drop down and you will be able to observe light which you're otherwise not able to see. And in particular, you can do this because dust is like reprocessing light of which is coming in the UV and the optical into infrared. And therefore, if we look at this cloud in infrared, we really start to see the cloud itself. So the cold gas, which has around 10 to 30 Kelvin or so, is really lightening up in the infrared. So this is now taking with Spitzer, so still relatively short wavelengths in the infrared, but you can also go, of course, a lot longer wavelengths nowadays, which has been done with Herschel, but then like 250 micron and so on. But then also with ALMA, you can go to a much longer wavelengths, which is then necessary to study what's going on inside these filaments and dense cores in detail. So basically the idea is the longer wavelengths you go, the deeper into some object you can see. And this is particularly relevant when you want to study star formation, because we go to super high densities, and therefore we can basically only see things at very long wavelengths in the radio. And you will see that we become optically thick actually in the infrared in the star formation process. So then I thought I'd give you just star formation in a nutshell. So what are we dealing with here? So as I said, we start typically with dark clouds, which are these molecular clouds. As you've just seen, the Orion cloud scales of several tens of parsec. And they have local density enhancements inside, which we call prestellar cores. And already here you can think about how the fragmentation of the cloud into cores proceeds. We know that clouds are supersonically turbulent on these larger scales. I will talk about turbulence later on. And then when we look inside one of these dense cores, eventually we have collected so much mass in gas that the object becomes locally self-gravitating and it starts to collapse. And if it does that, then it manages to form at least one or multiple protostars. We will also talk about multiplicity later on, which is usually surrounded by a protostellar disk. The reason for forming the disk is that you have usually non-zero angular momentum in the prestellar cores, and therefore when you collapse, angular momentum is conserved, meaning that you form a protostellar disk around the young stars. And accretion can then further continue through the protostellar disk by redistributing angular momentum inside the disk. So this is really disk physics, which is also relevant for star formation, because you need to understand how much of the mass of the disk is feeding actually onto the star. And also the process of how the mass is feeding onto the star is important, because you can see that we have indicated here such a jet and outflow. And this jet and outflow is thought to, come along when basically magnetic fields are winding up during the accretion process, and you can actually carry away a lot of angular momentum in the jet and outflow. About 90% of the angular momentum, which would be otherwise accreted onto the star, is carried away. And this is necessary in order not to spin up the star beyond breakup rotation. And then some fraction of the mass, which would otherwise accrete, is also carried away. And here we typically think it's about 10% of the mass, which is carried away in the outflow. However, these 10% of the mass is not everything which you will actually see coming out of the core, because there's a lot of entrained mass pushed out. Basically, the outflow is taking along all kinds of gas with it. All right, and so this whole process here happens on timescales of maybe 100,000 years or so, until we are finally, so this would be like a class 0 stage, where we maybe have already a little protostar inside, but everything is very deeply embedded. There's a lot of mass in this so-called envelope, so basically the leftover core. Then once the star and the disk has formed and we have less mass in the outer envelope, we'll speak about a class 1 object, and then about a class 2 when basically there's not much mass left in the envelope, but there's still a disk. And so basically these class 2 objects, then they exist for longer. Then we think that planet formation is happening in these prestellar disks, which we then in the end need to form planetary systems like our solar system. And currently the idea is that planet formation takes place on much longer timescales. So I think for me, this is really one of the grand challenges of numerical modeling, because you need to go to super small scales resolving the disks, and you have dust physics there and radiation and whatnot. But then on the other hand, if you want to model planet formation, you need to study these systems for millions of years. And, doing that in high resolution with short time steps and all of this physics is right now just still impossible. So people are doing tricks about this, but we don't talk about planet formation too much today. So I'm going to leave it at that. But I think this is really one of the big questions, how to actually end up with such a planetary system. All right. So while we are going along, we have also, due to the collapse, we are changing the density of the gas quite a lot. So in the prestellar cores, we have typical densities of about 10 to the minus 18 grams per cubic centimeter. That would be already like the center of the core. Maybe the outskirts have around 10 to minus 20 grams per cubic centimeter. So if you like to think about number densities instead of mass densities, you can think about 10 to the 4 to 10 to the 6 particles per cubic centimeter. But then if we collapse and we actually, before we even form a star, we form a first core. This is an object which is optically thick. We are here at densities of about 10 to the minus 12 grams per cubic centimeter. So this is at least 6 orders of magnitude in density, which we are going here. Finally, the star has a density of 1 gram per cubic centimeter. So there's another 12 orders of magnitude to go. But typically what we cannot even resolve these densities here in numerical simulations unless you do SPH or maybe a moving mesh. But with grid codes, this is already basically not achievable unless you have a specific spherical grid or you know, you spend a huge amount of time looking at one particular region. But the problem is that the time steps also drop so much, so you wouldn't be able to go on for very long. So people do like adaptive time stepping. Okay. And so then this is basically prototypical for like all cores and stars, but massive stars are particularly causing us a headache because there's so much mass in the core. We think that massive stars also form from massive cores. And if you think about star formation efficiencies in the cores, meaning that how much gas is actually turned into star, that's the star formation efficiency. Then if we say star formation efficiency is around 10%, maybe 50%, then yeah, in order to form like 10 solar mass star or so, of course, you also need 20 solar mass core or 50 solar mass core, something like this. And then it becomes even more demanding to do the simulations. The more gas you have, the denser you are typically overall. And this reduces again your time steps. All right. So then let's actually talk about what we can do or a little bit more about what we know. So actually, I find this really cool. This is a gallery of problems in Orion. So this is actually showing you that disk formation really happens, right? And so you can see here the disks, which are shown as these dark lanes, and they are basically in you know, there's light coming from the background and the disk is so optically thick basically to this light that it's absorbing it, and therefore you can see the disks in these dark dust lanes. And often you have movements, or you know, stars are pushing stuff around, so you get these bow shock types of configurations. So so these are really disks now on very small scale, so this is like 50 AU or below. So it shows you that this is actually working, this kind of model with angular momentum conservation. Right. And so we, in order to look at what prestellar cores look like, we can nowadays study molecular clouds in a lot of detail. So the current view is that we have the molecular cloud, which is overall already very rich in substructure. So it has filamentary substructure. It could also be sheet-like substructure. We are working on this a lot, also in simulations and observations. So it seems that there's like sheet-like structures on larger scales, and then condensing into filaments within the dense parts of the clouds, and then the filaments probably fragment into cores to some extent. And people have done a lot of statistics on cores. And this is one example. So this is a paper from Könnives et al. From 2020. And she studied the core mass function in Orion. And so you can see here actually, so the core mass function fit is this red line here. This is a log-normal fit. And what is plotted is basically the number of objects in a certain mass bin. The mass bins are in log. And here you have the mass also on the log scale. You can also bin per linear mass, but then the slope, of course, is different by 1. Okay, so sometimes you read minus 1.34 for the high mass and sometimes minus 2.34. This would be the typical salpeter slope. But the only difference is how you bin your objects, so in log or in linear space. So what she has now done here is that she basically looked at robust prestellar cores. So these are objects which are basically way above the detection limit, which is given here at about 0.4 solar masses or so. That's like the sensitivity and a limit of these observations. And then these are candidate prestellar cores. And here you see that there are lots of small structures which they think are starless cores, but it's not really clear whether they are real objects or just fluffy things. And so you can see that there are many of these. So I think in the future, when we get more sensitive observations, it will be important because you see that this peak of the distribution is just round about where we have the detection limit. And of course, it would be good to know whether there really is a peak or whether it would just continue, increasing for smaller scale objects, or whether these are fake objects which just don't really exist. And the more robust prestellar cores, which are pointed out here, are really more high mass. And this is important in the context that we want to understand how the core mass function maps into the stellar initial mass function. And so the stellar initial mass functions are now indicated here for different models. This is the Krupa IMF from 2001. So this is from Pavel Krupa. So you see that, and this is the Chabrier IMF. You see that they both agree on the high mass end. So this is the typical salpeter slope. So basically everything like beyond 1 solar mass or so is typically salpeter slope, and we think that this is very robust. But then if you go to smaller scales, it makes a difference whether you have power laws stitched together or whether you have a log normal function. Now, there is a difference here in any case because the Chabrier IMF is a system IMF, meaning that if you have a multiple system, binary, triple, etc., these masses are like counted together, while in the Krupa IMF he's trying to correct for that and only giving a mass function for individual stars. Of course, this is difficult because it's difficult to resolve very low mass stars. So there's some assumption here and here. In any case, you see that the peak of these distributions is around 0.1 solar masses or so, slightly lower than that, maybe. For Krupa, it's like 0.08 or so. So this number we need later on. That's why I'm pointing it out. Okay, so but if we just look at this again, we see that the CMF kind of resembles the IMF, right? I mean, at least you can fit both of them with a log normal to some extent. And this, of course, raised the notion that, perhaps the IMF is just a result of the CMF, meaning that there's a causal link between the distribution of cores and the mass distribution of stars. And this would work if every core would on average spawn about 3 stars or something like this. Of course, not all of the mass is going into stars. So there could be an offset because of a reduced star formation efficiency. Typically, the offset is quoted as a factor of 3 or so. So if you would have 30% star formation efficiency, you would be there, but only if each core would form a single star, which is not the case. So you also have to correct for multiplicity. So in the end, however, you could still do it, that you actually match the core mass function into an IMF. But whether this is really the case or not, I think is still an open question, and we will come back to this later on, because there are competing models, and I think probably this can only be resolved by both better simulations as well as also better observational studies. And there are programs going on right now with ALMA in this regard, like the ALMA IMF program, for example. So then multiplicity. I plot here the multiplicity frequency, which is defined as the number of primaries. So here a primary is a primary star in a multiple system, where in this case it does not matter how many stars are in this multiple system. So it could be 2 or 3 or more. But it's a good definition because it's quite a robust number actually in this regard. And so you divide this number of primaries by the number of singles plus primaries, and this gives you the multiplicity fraction in several mass bins. So if we plot here the mass again, and you see that the bins here are indicated, and the bins are like coming from observations, then the general trend we think is that the multiplicity frequency increases as a function of stellar mass, so it actually is it could almost be 1 for high mass stars. It's certainly quite high for high mass stars. That's what we think. The downside of this, you can see that these studies have been done quite some time ago, and I'm pretty sure there are updates now with Gaia, etc. But the downside of this is that most of these data is coming from for field stars. So these are very evolved stellar systems, and of course the stellar systems undergo n-body dynamical evolution over their lifetime, so to say. And this can also disrupt multiple systems and make binaries tighter and whatnot. So therefore, you take it with a grain of salt, okay? Because it could be that these lower mass systems are more easily dissolved than the higher mass systems or something like that. So I think here we could benefit from better statistics for young clusters, which needs to be done in more detail in the future. Yeah, but so this is like our general idea at the moment, that multiplicity increases when you go to higher mass stars. Right. So now let's talk about how we get multiple systems. And how to get multiple stellar systems. The only way to do this is to have fragmentation proceeding in your pre-stellar cores. And you can either have fragmentation you can either have fragmentation of the core itself, and we will see some examples of that, or you can have fragmentation in the disk later on. So so these are 2 different modes of fragmentation, which we have to take care of. Then what I wanted to show you here is what is actually happening with the fragmentation process. So these are 2 slightly complicated plots, but actually they're not so complicated. Just bear with me. So you have here the temperature and here the number density. And here, unfortunately, is the central density in grams per cubic centimeter. So this is particles, this is grams. And the range of the density on this plot starts about here, where I indicated this with this blue line. And what you see is how the temperature typically evolves as a function of density. So let's start from these very low densities here. So this is 1 particle per cubic centimeter. We just said the centers of our pre-stellar cores have around 10 to the 6 particles per cubic centimeter. So this would be pre-stellar core center here, basically. And these lines here are for different metallicities. So if we stick with solar metallicity, we look at the lowest line here. So you can see that with a lower metallicity, your temperatures increase because of the reduced cooling. Cooling over here is done via lines. Usually ionized carbon and atomic oxygen are the most important coolants here. And if you reduce your metallicity, then of course you have less of that. So you also have less cooling. And then just because we speak about cooling right now, so dust cooling would only become very important over here at these higher densities. So over here is really the line cooling regime. But I leave this to the ISM lectures, hopefully. All right, so you can see that so we end up with some basically quite low temperatures down here. So yeah, 10 Kelvin or even a little bit smaller than that. Here, over here, it starts with 10 Kelvin. And then, so when we reach densities of around 10 to the 5, 10 to the 6, the dust and the gas are very well coupled thermodynamically because you have relatively high densities, so you have constant collisions between dust and gas particles. And this allows the gas to transfer energy to the dust, and the dust radiates in the infrared. And this is how basically you can cool the system very efficiently. And you end up having around 10 Kelvin or so, which actually comes from the fact that you have heating in these regions by like cosmic rays mostly, because you're so dense that radiation cannot penetrate anymore. So it's mostly cosmic rays which heat like your cores. To around 7 or 8 or so Kelvin. And then you collapse further. And so this collapse can actually proceed almost isothermally, because you have this very efficient cooling by the dust. And this works very, very well until you hit the opacity limit. So once you hit the opacity limit, your dust becomes optically thick in the infrared, and then all of a sudden, like, this cooling breaks down, right? So this would happen at densities of around 10 to the 12 or so. So yeah, it's like indicated here. It could already start a little bit earlier, and then yeah, it would really start to be optically thick in this regime. And so basically what happens if you think about modeling, we think about an adiabatic index, which describes how our gas reacts to changes in pressure. Then we go from an adiabatic index, which is around 1 for the isothermal phase, to an adiabatic index, which is higher than 1, so about 5/3 or 7/5. This is for molecular gas. In this like regime where you cannot cool efficiently anymore. So it's basically adiabatic behavior. So what does this mean for the Jeans mass? So the Jeans mass scales with density to the -1/2 and temperature to the 3/2. So if we are in this isothermal regime, then our density increases, but our temperature does not change. This means that the Jeans mass drops with the density increasing, yeah, because of rho to the -1/2. And so that means that you drop your Jeans mass, drop, until you reach these densities here, where all of a sudden you start to heat up your gas. And then this T to the 3/2 really kicks in, and it makes your Jeans mass increase again. And you see that you become hotter and hotter as you go. There's another second isothermal collapse phase here, which is caused by the dissociation of molecular hydrogen in these very dense regions here from densities above 10 to the -8 grams per cc or so. You can also see it here. So in any case, you will further increase your Jeans mass. And so that means that at this point where you are at the opacity limit, you basically hit a minimum Jeans mass, because you have decreased your Jeans mass and then you increase it. And this means that you have a minimum Jeans mass just around at the opacity limit. And you can work out what this is. It's about 0.01 solar masses. And so this has been worked out actually a long time ago, like by Lowe and Lindenbell in 1976. However, the interesting thing now, if we go back to our IMF, we saw the peak of the IMF is higher than that. So the number of stars peaking at 0.08 or 0.1 solar masses means that you have factor of 10 or even more, depending on what IMF you choose. So that means that this minimum Jeans mass is not really setting the maximum mass of the stars, but it is definitely setting a limit. So it's difficult to form stars which are much lower mass, because otherwise, they would just not really collapse any further. And so this tells us this one thing: they're probably unlikely to have lower mass stars. So there are lower mass objects, but they are not really going through this process probably. So we think also that if you are around this limit, like that brown dwarfs form in disk fragmentation, for example, rather than core collapse. And it also tells us that it's not really the minimum Jeans mass which is stopping the collapse and leading to the peak of the IMF, but that there must be some other processes which kick in before the opacity limit. So these are the two things which are important here. But in any case, you can have fragmentation going on all the way until you hit the opacity limit very efficiently. All right, and so then when we also form disks when we are collapsing, and we have seen them in the observations before, and we know that they come along when you have angular momentum conservation during the collapse. And I just pointed out that probably brown dwarfs form in fragmenting disks. And there has been a lot of work actually coming from the galaxy scales about the stability of disks by Tumri, for example, who came up with a parameter Q, which is dimensionless and which describes the stability of disks. So you can apply it to galactic disks, but also to prestellar disks. The model just assumes that your disk is thin. Okay, so your disk should be infinitesimally thin in order for the disk to become unstable when Q is smaller than 1. For Keplerian disks, you can actually rewrite Q as the mass of the star divided by the mass of the disk, and then times the scale height of the disk divided by the radius. Scale height is given as the sound speed over the angular rotation frequency. And typically you actually have flaring disks, so they are thinner in the middle, and then they are like, they have a larger thickness when you go further out. But it's a bit compensated because you divide by R, and as you go further out, R also increases. But so you can see that basically if you have a lot of mass in the disk, Q is like pushed down, and then the disk overall becomes more unstable, right? So the more massive the disk is, the more unstable it becomes. And what we then typically see when you have gravitationally unstable disks, you form spiral arms, like in this simulation here. And the spiral arms then lead to, or in this process, you get gravitational torques, which allow the redistribution of angular momentum, and this allows for efficient accretion onto the central stars. There's one, so it's not so simple, because it's not like when you see in an observation or in a simulation that you can say, I see spiral arms, so it's gravitationally unstable. That's not really true, because you could also get spiral arms by perturbing the disk from the outside. So if you have a third companion, for example, flying through, then it can excite spiral arms in the disks because of torques. So this can also then, promote accretion and redistribute angular momentum. But so this is like the general picture for thin disks. And it's always a good estimate if you want to study whether your disk is unstable or not. Just compute the tumor parameter and check. There are modifications of this for thicker disks, but of course you have to make some assumptions then. Okay, then we speak about physical processes, other physical processes. So when we look at the gene's mass, basically we are only considering thermal pressure and gravity. We are not really considering anything else. So this is what you get when you do a perturbation analysis on the Euler equations. You can derive your gene's mass, but it's only thermal pressure and gravity. But there are also other physical processes which shape cores, and one of them is turbulence. And so, for example, I mean, we know that molecular clouds are turbulent. Why do we know that? Because we can observe molecular gas using molecular line tracers, and we can look at the width of the molecular lines, and we can easily find, when we look at molecular clouds, I don't have the slide here. Usually I can show you. It's very beautiful for Orion. Actually, you can see that there's a spread in velocity dispersions over about 10 kilometers per second or so. But if you work out what is the sound speed of the cold gas for 10 Kelvin, it's about 0.2 kilometers per second. So if you get a line width which is broader than your 0.2 kilometers per second, you can basically only attribute it to some non-thermal motions, right? And non-thermal motions very quickly in such low viscosity gas lead to turbulence, because you generate shocks and you get turbulent motions everywhere. And so the question is, how do the cores condense out of the lower density medium? How are they perturbed by the turbulent motions, which are on the larger scales in the molecular cloud? Do cores also show supersonic motions or not? So just one more word about the turbulence itself. So the, I think, best simulation to date about studying isothermal turbulence is this one here by Federat from 2021. They have a resolution of 10,048 cubed. So this is a grid simulation with flash, and the basically what they do is that they set up a box in such a way that they can have a driving scale where turbulence is being injected and driven. I think they use Mach number 4 or something like this, and then they want to resolve this so-called inertial range, which is where the turbulent power spectrum is established. They want to resolve it beyond the so-called sonic scale, which is the transition from supersonic motions to subsonic motions. So the idea is you drive the turbulence on the large scales, and then you basically have a Kolmogorov picture in mind. So the larger eddies turn into smaller eddies and so on. And this is how the turbulence decays to smaller and smaller scales. What we plot here is the spatial scale. So you go from large scales to small scales on the x-axis. And here is the turbulent Mach number. So we go from this forceful driving at Mach number of around 4 to, so we decay, the turbulence decay as we go to smaller scales. And at some point, depending on what is the temperature of your gas, you hit a Mach number of 1. So if we have our 10 Kelvin gas as in the molecular cloud, where we said the sound speed is 0.2 kilometer per second, then a Mach number of 1 would correspond to the turbulent velocity dispersion being equal to the sound speed, so 0.2 kilometer per second. And so this is where you transit from the supersonic to the subsonic regime. Now, what they find in this simulation, this is actually why they did it. So we know that in the subsonic regime, the Kolmogorov power spectrum should hold. So because actually the Kolmogorov theory is really only applicable for subsonic turbulence. But there are modifications to it in the supersonic regime, and you would get something like Berger's turbulence, which has a slightly steeper power law. And this is why they did the simulation, because they wanted to see whether there's really a transition of a slightly steeper to slightly flatter power law going from supersonic to subsonic. And this is what they actually find in these simulations. And then eventually down here, you have dissipation. And dissipation, when you do these numerical simulations, of course, you're never resolving the actual viscous dissipation scale. You're always dominated by numerical dissipation. So you basically are limited by resolution. So if I do not do crazy 10,048 cubed, but I only do my typical 128 cubed or whatever, what it means is that I would not be able to resolve any of that, because you basically cut off at much, you have a much smaller dynamical range. Yeah. And so then you would already see here a transition where you basically lose the turbulence. So this makes it tricky to actually study what is the initial condition for your star formation in pre-stellar cores, because what you would really want to do is you would want to have such a simulation of a molecular cloud and look at the molecular cores which are forming inside, and you actually would want to resolve the cores with such a good resolution that the turbulence inside the cores is actually modeled properly. And this requires really high resolution. And so therefore, I think to date, we haven't really managed to do this. Just one word of caution, because of course it's then beneficial to use adaptive mesh refinement codes or to use SPH codes and so on, but we have played a lot with this. And so you have to be really careful how you refine, because if you wait for too long, the turbulence doesn't wait for you. It's just dissipating like crazy on its dissipation timescale. And so if you basically wait too long for resolving some patches with higher resolution, it's already gone. Your turbulence is dissipated. So what we saw when we wait for long before we refine is that we get rotating blobby structures with a lot of like solenoidal motions, because the angular momentum does not go away, but the shocks are going away, the shocks are gone. And so So I think, you know, all of these simulations with used genes refinement and like wait for long before they zoom in, they are very good and nice, but we still have to do better. I think we still have to really try to resolve the larger scales better and then zoom in, you know, with higher resolution before we actually zoom in onto star formation just according to gravity. Okay, having said this, so there is one more thing I want to talk about before we make a short break. So it seems that, and now this is not a result from simulations, because otherwise it would be a bit, yeah, you would have to think about whether it's right or not. But this is from observations. So it seems that the cores are showing, basically cores are objects which are forming right around where you transit from the supersonic to the subsonic scale. Or actually, we don't know whether it's right around here or whether it's further down, because once you are below sonic, you're dominated by your sonic line width, so you cannot see how much basically the turbulence contributes very well. So, but there seems to be a transition to coherence, meaning that within your prestellar cores, your turbulent motions are not supersonic anymore, but they're rather on the sonic scale. And there have been actually, this has been found first by Alyssa Goodman in 1998, but then there have been a lot of recent works also looking at this in detail by Pineda, Chen, and Chaudhuri, for example. This is from the Chaudhuri paper where they looked at a number of cores. Right. And so it seems that, you know, these cores are maybe more coherent islands, so to say, in the molecular clouds, which would motivate that we could use cores as isolated initial conditions for studying star formation. However, just because they are islands doesn't mean that they are, you know, isolated. So they are still like accreting and interacting with the environment. And there was one last thing I wanted to say to this. So actually, I wanted to point out that turbulence in general is always associated with angular momentum in the cores. So, so what we have done in an experiment was that we took a prestellar core, and what you usually do to drive turbulence is you apply turbulent velocity fluctuations which follow a turbulent power spectrum, as we've just seen it, onto your core. And so what I tried here is that I basically chose different largest scales. So you could, so basically it was like, okay, what do I actually do? I mean, you could perturb your core on the scale of the diameter. You could perturb your core on the scale of the radius. You could perturb it on a larger scale, right? And then you would only get a fraction of the fluctuation inside. And it turns out that it actually matters how much specific angular momentum you generate in your initial condition, depending on how you introduce your turbulence onto the core. So because if you perturb, it's actually logic if you think about it. So if you perturb on a very large scale, so this is this largest scale basically, the smaller it is, the larger it is. So if you perturb on very large scales, then you have like one big solenoidal mode, so to say, on the core, which means it's like, you know, swirling with a very large radius of the spoon, right? And so then you generate quite a lot of angular momentum. But if you only do little swirls inside the core, then you generate much less net angular momentum. And you can, in this way, actually find that your initial condition doesn't only depend on the virial parameter, so the strength of the turbulence compared to gravity, but it also depends on how exactly you set up your turbulence, because this will change what kind of disks you're forming, because you have this angular momentum, no matter what you do, right? It will be conserved unless your code is wrong. And so then it will go somewhere and it will form a disk. And so this is what we will look at later on when we look at the results. Okay, so this is a takeaway message because I think many people don't know this. Right, and maybe then I do one slide because then I'm actually on to the next modeling thingy. So then we talked about turbulence. what about, and another physical process, of course, which we have is magnetic fields. And so here we can estimate the role of magnetic fields for core collapse by looking at this magnetic mass to flux ratio. So this is basically telling us how strong the magnetic field is and whether it is strong enough in order to stabilize the core against collapse. So there's a critical ratio which you can work out, which is given by this formula here. Basically, if you have cores which have a magnetic field strength that is lower than the critical value, then you actually call these cores supercritical. It's a bit counterintuitive, but it means that the mass is basically larger than what you would have as a mass in this critical core. So supercritical means magnetic fields are small, so not very important. Subcritical cores, your mass is basically small compared to this critical ratio, and therefore your magnetic fields are important and can probably stabilize cores. So there has been a lot of work on this by Moscovias and so on, going back to the 80s. I found this paper here interesting, the one by Chen and Oestreicher, where they compute a magnetic Jeans mass. This is for spherical systems, but you can see that it's kind of a Jeans mass criterion, which depends on the magnetic field strength. And in this way, you can work out what kind of, you can estimate whether the cores which you form in the simulations as they've done here, whether they have critical masses or not. An interesting recent result is by Felix Priestley. He was using molecular gas chemistry in order to figure out what is really happening in prestellar cores. And so for that, he was looking at molecules which freeze out of the gas phase. So for example, CS and HCN do that, but I'm not such a molecular specialist. I'm pretty sure there are much better people here about this. But anyway, so freeze out takes also some time. And so it means that the longer time you have before you actually collapse your core, the more freeze out you will have. And so basically when you have very magnetized cores, so close to subcritical, if you're really subcritical, they don't collapse anymore very efficiently. But so if you have strong magnetic fields, you have longer collapse times, and therefore you would observe lower intensities of CS and HCN because you observe these intensities from molecules which are in the gas phase, but when they are frozen out onto dust grains, they're basically gone, right? They don't emit anymore. So, so therefore the intensity reduces as you have longer collapse times. And also he found that the line widths in subcritical cores are more narrow. And so overall, he concludes that these lower intensities and more narrow line widths are better fit to observations. So this hints towards actually magnetic fields playing an important role for prestellar cores. If magnetic fields play an important role, we are right away at the non-ideal MHD effect question, because these estimates are based on ideal MHD, meaning that you assume that the gas is perfectly coupled to the magnetic field, so to say. So the magnetic field lines are frozen into the gas, and gas can only flow along the magnetic field lines. But if you have non-ideal MHD effects, like for example, ambipolar diffusion, you can have only the ions coupled to the magnetic field while the neutrals don't. And if you have not 100% ionization fraction, but also a lot of neutral gas in your cores, then the neutral gas can basically collapse while the ionized gas stays behind. So that's very simply said. And so there are actually three non-ideal MHD effects, but for the core scales, I think ambipolar diffusion is the most important one. Okay, and so then I would break here and ask for questions, and then we will move on with modeling. Yes. Yeah.
Are magnetic fields more important in higher mass cores because you also have higher temperatures?
I think it would be actually the opposite. So if you have higher temperatures, generally you have higher ionization fractions. And then, yeah, the higher your ionization fraction, the better you have coupling between magnetic field and gas. But it's a good question. So I'm pretty sure because you go through such dense stages when you form massive stars that there must also be a regime where you know, non-ideal MHD effects are very important. So I think it's in both. I wouldn't say it's more or less important. It's probably same, I would say. Yeah.
Any other question on this first part? So most of the stuff you've shown are for our galaxy, right?
Mm-hmm.
Can you comment on what happens on galaxy with low metallicity for star formation?
Mm. Yeah, so I only showed this one plot for low metallicity, right? Yeah, here. Yeah, so all right. So I mean, this is basically showing the temperature evolution as a function of density for lower metallicity. And you can see that because the cooling is less efficient, you would generally have higher temperatures in the lower metallicity gas compared to solar metallicity. So what it means is that generally fragmentation should be suppressed when you go to lower metallicity systems. Yeah, however, there are also like then other ways to fragment. So I think in terms of POP3 star formation, I think the general notion is that you would get a top-heavy IMF, but it's not clear how top-heavy it will be. So I think also for that, we would need much better models. Unfortunately, it's impossible to observe this. So for that, we really need to rely on good numerical models there. But so there's work by Dan Whalen, for example, and for POP3 star formation, they find top-heavy IMFs. Yeah, but I also would like to say that in general, these very low metallicities are really only for the first generation of stars. So metal enrichment in galaxies is typically very fast. And already at high redshifts in more massive galaxies, so the ones which can be observed nowadays, you have almost solar metallicity. Yeah. So the enrichment is very quick apparently. And in order to study low metallicity systems, it's best to go to nearby dwarf galaxies, where some of them have very low metallicities. Yeah.
Christina?
I was reading into massive star formation theories a couple months ago, and it seems like there's two competing theories, and I was wondering if you knew about them, and if you did, if you could help summarize, because this is a very big field that I know very little about.
Yeah, that's right. So there's a very big field, that's right. So yeah, so basically you have either turbulent fragmentation, meaning that in this case, you would form massive stars only from massive cores, or you have competitive accretion. This is from, you know, the Ian Bonnell work, where basically you could also form a massive star from a slightly lower mass initial condition, but then you like accrete a lot of mass and eat it away from other sources. And yeah, so these are like the two models in a nutshell. And I think probably the answer is somewhere in between. There has been recent work, I point out at the end, by Haugbolle from, you know, Denmark, and Pelkonen had a paper in 21 where they basically say that there's a statistical relation between the core mass function and the IMF, but not a direct relation. And so it's kind of something in between the two scenarios. But I think this question is also related to when massive stars form and where. I think we still don't know these answers in detail. Yes. Yep.
What about the rapid versus slow star formation or the low efficiency? Maybe that was the huge control. I mean, that was a bigger fight in star formation, I think.
So I suppose that Melanie will talk more about this on Monday. But I have a talk about this, but not here. So I think the notion nowadays from galactic observations, like if you go to scales of several hundred parsec, you get very low star formation efficiencies, right? And then if you go, then the question was always, is it also so low in the prestellar cores or in the molecular clouds or not? Or is this formation of molecular clouds itself inefficient, or this collapse of molecular clouds? And so it seems that the cloud lifetime is actually short, only about 10 mega years or so, while the depletion time on the large scales is about a giga-year. So that means that probably molecular clouds form fast and are dispersed also quickly. And I think this hints towards the fact that stellar feedback is very efficient in dispersing molecular clouds and reducing your star formation efficiency locally. At least that would be my conclusion to this.
Okay, good.
Yeah, she will talk about it on Monday. Okay, very good.
So you will get more about the controversy.
So we could have a short question before we hit the hour. Otherwise, I think we might as well continue. Yeah.
Okay, good. Do I go forward or backward? Now I go forward. Okay. Right. So now let's talk about simulations. And okay, we have 45 minutes, right? So I'm not gonna give you all the nitty-gritty details, but let's see how far we get. So so how to model star formation? So very general. Actually, you're doing simulations yourself at the moment in the hands-on sessions. So at least some of you. So therefore, you probably know already a lot about this. I just want to point out, of course, we have two different possibilities to describe our gaseous system. So one method which has been used in the early star formation simulations is SPH. So this is the Lagrangian approach where basically you split up your gas into particles which have typically equal mass. You don't need to have equal mass, but equal mass gives the best properties numerically. So that's why people use equal mass particles, unless you do particle splitting or something. But in this patch, which you're interested in, equal mass. And then basically the particles are representing parcels of gas, and they are moving around with the flow, so they are moving the mass around. The advantage of this is that it's intrinsically adaptive. That's what the Lagrangian approach is. So if you concentrate your mass towards some common center, which is happening in star formation, then of course the particles will all flow there. So you increase your resolution as you go along. And this is cool because it means that you can resolve the star forming cores in the centers. You can resolve the disks quite well, which are relatively massive. But you cannot resolve very well low density gas, of course, because there you lose the resolution. And so I think SPH is still very good when you want to study prestellar collapse. It's not so good when you want to model turbulence or like the interaction in general of high density and low density gas, just simply of how the particles interact with each other. Because what you actually do, and this is why it's called smooth particle hydrodynamics. So it's not like each particle is on its own, but each particle interacts with other particles, their neighbor particles, and the gaseous properties, so density, velocity, and so on, they are smoothed over the so-called smoothing kernel. And you require to have a number of particles in your kernel, typically at least 50, in order to reduce the statistical noise. And so then, you know, you would basically have to interact with your neighboring particles in order to compute your properties. And so imagine you have a lot of neighbor particles on this one side, but very few particles on the other side. But because your kernel is spherically symmetric, you wouldn't actually account for this. So you would find a lot of particles on this side. So you're very biased towards this side where you have many particles, but you don't find many on the other side. And so then, however, if you do just a normal averaging, you basically you almost ignore these, right? And so you don't interact very well with the low density environment. And this is generally the problem. So then there are ways and methods to try to fix this. And I think SPH has improved a lot. For example, one can also compute Riemann fluxes across the particle interfaces and so on. Yeah, so I think in general, it's a very good method if you have a high dynamic range in density and spatial scale. And then there is the Eulerian approach where you take your volume and you just split it up into cells. You can do this in 2D, 3D, even 1D. Yeah, also SPH you can do in all dimensions if you want. And you can have then something called mesh refinement or adaptive mesh refinement, where basically you have criteria which define what you find interesting. And then locally you increase your resolution based on these criteria. And we call it adaptive mesh refinement if the refined mesh is actually moving around with the interesting area. Meaning that, say, you have here a prestellar object and it's moving around, then in the next time step, I would have to resolve these cells here with higher resolution and then these and so on and so forth. So it means that your mesh is changing continuously. This is some overhead work. It can also, if not done carefully, introduce noise. So this has to be done very carefully. And also, if you are very restrictive with your adaptive refinement, you can lose information. So you should always make sure that you refine early enough, so to say. So this means, waking up cells which are nearby and telling them, oops, something is coming, be careful. We had some fun with gravity in the early versions of Flash, where basically the blob was overtaking itself and then it was decelerating itself and whatnot. So it was like really crazy. So this has to be done carefully. But similarly, also carefully here, you have to wake up other particles which are interacting. Say, if a shock is coming along, you have to make the particles aware of that something is coming along. And so that's always something to think about in both approaches. So in general, then grid codes, of course, you solve mass fluxes across each of these interfaces. You do this by solving a Riemann problem. So you basically treat each interface as a little shock. And this gives you the flux of mass, momentum, and energy. So you're solving the hydrodynamically equations, so the Euler equations. And usually these codes are good for much better than SPH for high density contrasts, because, well, you just have interfaces no matter what. However, they are not so good for the dynamic range, because if you want to really zoom in on something, you need to introduce more and more and more cells, and then it becomes very quickly very expensive. So the typical star formation simulations you see, they go maybe from densities of 10 to the minus 18 or so to 10 to the minus 15. That's already for a grid code a very demanding simulation, but this is still 3 orders of magnitudes above the opacity limit. Yeah. So while with SPH you can take 100,000 particles and do a beautiful simulation where you resolve the opacity limit and done. I mean, so it's it's always a trade-off, I would say, what you want to do. So it's worth improving these codes, I would say, and improving not only the code, but actually the numerical method behind it in the future. And of course, there's something in between, which is moving mesh, which is the repo code, for example. which we talk about in a sec. So what do we want to simulate in order to simulate star formation? So we have the evolution of the gas, so hydrodynamics. We have magnetic fields, as we've just seen, so MHD. We also need self-gravity, obviously, otherwise there's no collapse. Then we have turbulence. We have talked about it. We have also, if we want to now look in a bit more detail, so not be isothermal and then switch to another equation of state, which we just put in by hand, then we actually want to look at the gas chemistry. So we want to understand how many neutral species are there, how many ions, electrons, dust, and so on. This is important as soon as you talk about non-ideal MHD effects. In particular, you want to know the neutrals and ions. You want to know the dust for the cooling. You want to know the cosmic rays and how they are maybe attenuated for the temperature inside the core. You also want to know the metallicity, because you need to know how many, how much cooling we have, what kind of molecules we can form, and so on. And in terms of star formation, we have seen that the stars are surrounded by disks, and actually, if you think that it's hard to resolve the star formation process, it's even harder to resolve the disks, because the disks are only resolved when you actually resolve the disk scale height. Yeah, I would say at least with 10 resolution elements or so. 10 is not much, right? So 10 is like the smallest number probably we should do. But the disks can be very thin because they cool efficiently and they become thin. And so basically it means that you want to have resolutions of, I think, much less than 0.1 AU to get the disk dynamics properly. And we will talk about why we need this later on, because the accretion physics actually drives the outflows, which probably set the peak of the IMF. So it's like, you know, all connected. Okay, then if we have stars in general, but in particular also massive stars, we want not only these physical processes, but we also want radiative transfer. So for the cooling of by dust and so on, we can still say, okay, it's optically thin, so we cool, the energy just escapes. But if we actually start to heat the surrounding gas and dust by the radiation from the stars, or even ionize it when we have more massive stars, then we really need to do the radiative transfer. And this is another complication to the numerical simulations. Just to give you some numbers. So usually the radiative transfer takes at least half of the simulation time, if not more. So this is like very expensive, even if you have very optimized codes. Okay, so so basically, yeah, we want all of this. And so this would be then our wish list. And in particular, we want to have everything coupled together, and we want to evolve it for a long time. And the question is this really possible? So let's talk a little bit about this coupling. So need to show you some equations, right? So that, okay. So what is this? So these are the ideal MHD equations and self-gravity. So ideal means already simplification, no non-ideal terms, and also only one fluid. So one fluid meaning one density, one velocity field. So if you want to have ions and neutrals treated properly and separately, you would immediately have different velocity fields and so on. So it makes it much more complicated. So then basically we have here our standard equation, so continuity equation. So this is the conservation of mass. So if you think about the grid structure, which I showed you before, every time I transport something across an interface, I want to make sure that mass is conserved. I don't want to lose mass. I don't want to gain mass while doing that. And similarly with the conservation of momentum and the conservation of total energy. So it's always the total energy which is conserved, not the kinetic one, not the internal one, only the total one, meaning that the total energy needs to be computed. And this is usually then done by summing up over all the energies we have. So we have always internal and kinetic. If we have magnetic fields, we also have a magnetic energy. And so there's one thing I want to point out here. So what you do is you solve your total energy, you have your new total energy. then how do you get now these individual energies? So you get your kinetic energy from basically from the velocity, which comes from the momentum equation. So there's no way to argue about it, right? So this is just 1/2 v squared times rho, if depending on what units you're using. So this is your kinetic energy. So that's set. Your magnetic energy is also set because your induction equation gives you the magnetic field. And well, okay, we can argue about whether we make divergence errors or not. Fine, but in the end, you don't want to screw up the magnetic field by changing the magnetic energy. So this is also kind of set. So the only thing which is not set by other means is the internal energy, and that's why it's a very poor energy, because it has to take all the crap from the others. So the internal energy receives all the numerical errors. All right. So therefore, because basically how you get it is you subtract the kinetic and the magnetic energy from the total energy, and the rest, the leftovers, so to say, is here, take this. This is your internal energy. So, but I mean, you do have numerical errors. You make them no matter what you do. And yeah, so therefore you have to be a little bit careful about that you actually make them as small as possible in order not to get crap pressures and temperatures out. And in particular, you don't want to have negative pressure. I mean, that's like the worst. But it can happen, right? So then there are some very bad fixes for this. Like, for example, okay, afterwards I say, well, I know that my gas is isothermal, so I set it to 10 Kelvin anyway. But just be aware when you run these schemes, there is an error and it goes somewhere, and it's good to know where your error is. Good. Okay, so these are our equations. Then I will not talk too much about this one here. I mean, this is an intrinsic constraint that there are no magnetic monopoles, divergence P equals 0, and it's not explicitly included in the other equations, and that's why it causes us some headaches, because we have to take care of it. And there are different ways to do this, either by divergence cleaning, like, the cleaning trip is going through afterwards and sweeping out all the divergence errors, or you can also do something called constrained transport, which makes sure that across the interface where you transport your mass, energy, momentum, your divergence P equals 0 condition is fulfilled. It's not necessarily true if you then look at the centers of the cells that there also divergence P is equal to 0, depends on how you compute it. But I will leave you to Eva for these questions. All right, then you also need a closure relation which relates pressure and density and internal energy. So this is for ideal gas, what we typically use. And we also have here, for example, in these equations, the gravitational acceleration, that's the only thing I introduced here as an extra force apart from the pressure force, which you of course always have, and the Lorentz force, which is this term. So this is the gravitational acceleration, and it comes from the gravitational potential, which needs to be computed via the Poisson equation. And so just one takeaway message before we move on. So first of all, this is a set of PDEs, so partial differential equations, and you can solve them locally. So we can locally look at the fluxes across our interfaces, yeah? And there's no dependence on any large scale effect. Large scale meaning other parts of the grid, which are not immediately at my interface. So of course, depends on the order of the scheme, how many cells you want to consider and so on. But still, you are local in this approach. Now, when it comes to the gravitational acceleration, we are not local anymore because we solve Poisson equation, and that's an elliptical differential equation. And because it is an elliptical differential equation, basically the solution depends on the whole field. So the solution for the gravitational potential depends on the density everywhere in the computational domain. And it's just because a different type of differential equation. And this is also why gravity is so tricky to solve. Nowadays, nobody talks about it anymore too much, because there are good codes around and good ideas how to do it. But this used to be a huge thing, still in like around 2005, 6, and so on. And it's still also very expensive due to that. In particular, if you do your calculations on big computing clusters, which have many thousand CPUs and distributed memory. Now, the problem is due to this global dependence, basically, once you change the density somewhere, you need to communicate this to everywhere else in your computational domain. And this requires a lot of communication between the different compute nodes. And this communication can easily slow down your code substantially unless you really take care of how you do it. So parallelization is a big issue when it comes to gravity, while it is actually not so much of an issue here. So if you see scaling tests where people present just hydrodynamics, if you have to review compute proposals, right? If someone just presents hydrodynamics, says, I have ideal, strong scaling, weak scaling, everything, it doesn't mean anything if it's only the hydrodynamics, unless they only want to do a hydrodynamic simulation, because getting scaling for this part is very easy. Getting scaling for other parts like gravity and radiation transport is actually much more difficult. Yeah. Because of the way the equation is given. All right. So there are ways to deal with gravity. And one of them is to basically use Green's function to rewrite the Poisson equation into basically using the Newtonian potential as the Green's function. And then in this way, you can basically turn it into a simple summation problem. And also what one can use in order to speed up gravity is to make use of the fact that the effect of the gravity scales with 1/r². So if a tiny little blob like a star is moving, but it's far away, then it doesn't really matter too much whether it is exactly at this place down here, or maybe a little bit further to the left or a little bit further to the left. It doesn't matter so much. It just matters that there is something and it is maybe moving. So basically what makes use of this are these so-called tree codes, where you basically you have your computational domain, which is split up into different regions and cells. There are different ways to do this. There are octrees, which basically split up exactly in half every time you split cells. There are also binary trees, which make sure that you split like number of particles and so on. So there are different trees. But the idea is always the same. So you have one root level, which is like the whole box. And then you split up your domain into smaller and smaller boxes. And until you reach the finest level, which is the leaf level. So the leaf nodes are on the finest level. And then when you want to compute the gravitational potential, what you do is that you walk the tree. So you basically collect all the contributions to your summation for each level, so to say. And then you have some criteria which define whether, when you want to compute the gravitational potential down here, whether it's enough information to have the information from this parent node, or whether you really want to have more detailed information going down maybe to this level or maybe even to the smallest level. So and basically these criteria often depend on how far this node is away. So basically if the node is very far away, then instead of summing over all the little contributions down here, which is a lot of work, I only sum over the whole mass distribution, which is collected in this larger node. And in this way, I only do one summation instead of maybe many hundreds or thousands. And this speeds up my code significantly. And you go from an n² scaling to an n log n scaling, which for large n is a lot faster. right? So then, yeah, I will not talk about this too much. You also have to think about boundary conditions, but I'm not going to talk about this now, I think. All right, let's talk a little bit about what codes we have. So we already talked about the different techniques. So for the grid codes or adaptive mesh refining codes, we have typically Ramses, which I think you're doing an exercise with. There's also Flash. There's ENSO, for example, Athena++, and Orion, and so on. Most of the codes nowadays are publicly available, which is great. And in general, what you get from these grid codes to summarize are relatively accurate solutions with good convergence, because the order of the scheme actually gives you the error convergence. So typically all of these schemes are second order in space and time, which means that when you go to higher resolution, your error would decrease by a square, yeah? So if you go down by a factor of 2 or up by a factor of 2 in resolution, your error decreases by a factor of 4, and so on. There are also other codes which are mostly used in aerodynamics, for example. They go to very high orders, 8th order, whatever. There are schemes like this, like Wino schemes or Ino schemes or discontinuous Galerkin schemes. Why do we still use these second order schemes? To be honest, when you have shocks, and we have typically shocks everywhere, then you need dissipation. And when you have very high order schemes, they are almost too accurate. I can't believe that I'm saying this because I always want to have as accurate schemes as possible. But if you have a shock and you don't have a way to dissipate energy when you encounter the shock, then the scheme will just explode. You will get fluctuations, and you will get negative densities, negative pressures, and it's basically over. All right, so dead. So what all of these, so then there's Pluto, for example, which has a higher order scheme. But even in these schemes, when you encounter higher Mach numbers, and here with shock, we are not speaking about Mach 10. A shock for these higher order schemes is already very close to Mach 1 and actually slightly below Mach 1. Then they already start to say, this is too much for me, I don't want this. So, so basically what these schemes do is that then they switch to lower order. All right, so and then effectively you don't get much better than second order or third order. So just be careful with these things. Right. So I think it's also worth working on this in the future, because if we do manage to get better schemes with higher order and higher accuracy, we save resolution, and this means we save computational time, right? Because if I converge more quickly and I get the same resolution, I get the same solution for factor 4 or whatever lower resolution, that's amazing. I mean, you save so much time, you can't even imagine that. So it's worth working on this. But so for now, second order. So the problem then is that we need a high dynamic range for star formation, and it's very hard to get that with the grid codes. Then smooth particle hydrodynamics, we have Gadget, of course, which is still around. There's also Phantom, which is quite a good code from Dan Price. Just due to the method itself, SPH has a bad convergence behavior. It only converges with the number of particles to the 1/2. And so this means that, yeah, you need to put in a lot more particles. So, I mean, you know, this is a power of 4 compared to what we have here with the second order scheme, right? So convergence is really bad. So I think it's worth thinking about whether the problem you want to do can be done with the number of particles you can afford. But if you say, no, I would need much more, then it becomes difficult. So that's the takeaway message. They are quite dissipative, so the standard SPH schemes, but they also have very good properties, namely they are highly adaptive. They have typically symplectic time integration, which means that they exactly conserve angular momentum, and so on. And so in particular, angular momentum conservation can be an issue with grid codes if not done carefully. There are no grid artifacts in SPH. That's why the movies always look very nice. And however, there are some problems with magnetic fields, although I think Phantom is doing this very well. So people are working on this actively. There are improved SPH schemes, which I think are also very promising. So Gandalf, for example, implemented a Riemann SPH solver, which actually solves the Riemann problem across particle interfaces. So it's kind of a mix between SPH and a Riemann scheme, so grid. There's GISM2, which implements meshless finite mass, respectively meshless finite volume scheme, which is based on a paper by Gaborov. The magnetic field implementation, however, is only proven for MFV. So if you check this paper, you can see that. And there's a moving mesh code, a repo at the moment, the most common one. I think Rowan probably showed some stuff with it yesterday. It's highly adaptive. It's based on a gadget in the very beginning, but by now I think they've done so much rewrite that it's not anymore gadget. But it used to come from gadget, so it is keeping the adaptivity properties, it is based on a Voronoi mesh, so this makes implementations of new physics a bit difficult. However, if you have everything which you need, I think it's a great code to use. Okay, and then in all codes, I think one needs to think about adaptive time stepping, etc. And also about, and this is the last thing I want to say when I go back one more time, one has to think about how to put in the other physics. So we're talking here about, okay, we had now MHD and self-gravity, but what about heating, cooling, and radiative transfer and so on? So basically what I need to do is I need to add more source terms here on the right-hand side. So for example, I can add here the momentum transport by radiation. I can add in the energy equation, I can add sources of internal energy, so heating or sinks, cooling. But the question is, do I get all of these gravity and radiation and so on? Do I get this at the same time as I get everything else, which means I would need to solve everything together? Or do I get this from some little bit offset time? Or do I get it from the old solution? I plug it in here and get the new solution. This is what's typically done. This is called operator splitting. So because the equations are so different for radiation transport, for gravity, for hydrodynamics, what you typically do is that you compute the solution, then you compute the acceleration by radiation pressure, for example, you compute the acceleration by gravity and so on, and you use this to compute the solution for the next time step. Yeah, so that means that yeah, you're basically not updating all of these accelerations at the same time as you're updating the solution itself. And this is called operator splitting, and it actually screws up your convergence order. All right. So let's not talk about this further because we don't want to talk about this, but yeah, I leave it at that. Okay. Let's talk about more fun things. So namely how to simulate star formation. And so we have discussed that cores are islands of, you know, quiescent turbulent motions, and maybe they are stabilized by magnetic fields, maybe not. So here are some prototypical cores. This is Bonar 68, like the prototypical Bonner-Ebert sphere, where Bonner-Ebert sphere is a sphere in hydrostatic equilibrium, which is stabilized by external pressure. And so the density profile would look something like this. So you have a flat inner part, and then the outer part drops off as r to the -2. You can estimate for pressureless collapse the time scale it would take to collapse. That's the free fall time scale. And so the question is, do they really sit there for some time? Then you would maybe get a Bonner-Ebert sphere, which is stabilized, and you push it a little further, then it collapses. Or do they evolve on short time scales, these cores? Let's see. So what happens when we actually do some star formation simulation? So I now show you some movie just to wake you up. In case it works, let's see. Okay. So this is a very simple simulation of a turbulent core. It has 1.3 solar masses. I don't know why it shows 1.3. It was my favorite mass in Ophiuchus, my favorite core. So, and it has turbulence. So basically, as it collapses, you see here the scale is 4,000 AU across. And this is the density field, which is shown. And so you can see that there are these filamentary structures which are feeding the central dense core. I mean, the core inside the core, so to say. And this is where star formation happens. And in these simulations, I told you before, you can do an SPH simulation with actually quite good resolution. And this was already possible to do 10 years ago. So we had here a mass resolution of 10 to the -5 solar masses. So that means that the resolution is much better than 1 AU in these simulations. The downside is there's not much physics. It's just hydrodynamics and gravity. And then there's some effective equation of state, which lets us model the disks. Okay, so if you have a turbulent core, which is collapsing, you see these filamentary structures forming. That's the typical thing you get. And so then I showed you before that it depends on your initial turbulent velocity field, how you generate angular momentum in the cores. And so it actually also depends on your initial turbulent velocity field, how you generate these filamentary structures inside the cores. And so we worked out that, in fact, you can, just from a very simple force balance, where you look at the ratio of centrifugal over gravitational force, you can figure out where filaments will form based on your initial condition. So, so what is shown here is this force balance, and what is shown here is the resulting density structure which formed. And so you can see that in regions where your centrifugal force was much smaller than the gravitational force from the very beginning, these are like the motorways where collapse will happen first. And this is how you enable the formation of these filamentary structures, because the filamentary structures are the lanes inside the core where collapse is easily happening while it is stabilized in other regions. This is basically what your turbulence does to your core. And so depending on how large scale your turbulent motions are, you get more prominent filaments, or you can also get no filaments at all. So going from these large scale turbulent fluctuations to smaller and smaller and smaller scale fluctuations. So here you see it's basically noise. Then you do not form these prominent filaments anymore. So this is the actual result of your choice of initial condition. And now if we zoom in into the core and see what's happening there. Maybe I'll show you the next movie. I think that's more interesting. Yeah, this one. This is my favorite one. This is another one, but another turbulent seed. So also you need to do many realizations because the turbulence is random to some extent. And depending on what you do, you get different outcomes. So here we zoom in onto the center. This is 400 AU across. You see there's a lot of turbulent infall. There's a disk forming and actually a binary in the center. And the disk is fed from these filamentary streams. And so it becomes gravitationally unstable. It's wobbling around and it forms another star in a minute. There you go. There it is. So these things are introduced at densities of 10 to the -11 grams per cc, so above the opacity limit. And now, due to turbulent infall, the disk rotation axis has actually flipped completely. So here you see it now face on instead of edge on as it was before. So now I thought, okay, stable disk, binary, done. The third one we just lost due to n-body interaction, but now it comes back. So there's also some gravitational instability. This is now really due to the disk being massive. So this gravitational instability was because of Tumori Q being small. And now here we have the companion coming back. And it really excites gravitational torques in the disk and causes these spiral arm features. And in the process, it's losing angular momentum because it's giving part of that to the disk. And so in this way, it's now captured. So there's dissipation. And so now we have a triple. And probably people who have looked at N-body dynamics know triples are very rarely actually stable. So this one is also not stable. So it will dissolve. Zack. And now we are left with a binary and a single star. And this binary has some leftover disk, but it's very low mass now at this point. Right. So this would be, I think, more like a typical star formation scenario, because actually stars rarely form alone. Most stars, there's nice work by Charlie Lauder. Most stars form in binaries or multiple systems. And so looking at in more detail, longer term evolution and with more physics, how such multiplicity affects also the evolution of the disks and the possibility to form planets in the disks. I think that that's really a cool thing, which I hope will be done in the next years by you guys. So, okay, so then a little bit more about initial conditions. So I wanted to point out some works, because right now we only talked about the turbulence, but actually also the density profile really matters. So there has been early work by Alan Boss already in 1987, where he showed that when cores are basically uniform density, they are much more prone to fragmentation than if they are centrally condensed. And in particular, if they have like power law profiles, like these plumber type profiles, then they are very robust against fragmentation. That's what he found. And Philip Gerichidis also followed up on this work in 2010, and he found the same result, basically. So the flatter the density profile, the more likely it is to get fragmentation. I mean, it makes sense, right? You have much more mass distributed everywhere. And so your turbulence can make little seeds, and you can like get a lot of fragmentation. While if you have something which has already a concentration of mass, you also, if you form fragments in your core, they must be self-contained, so stable against being stretched apart by the gravitational pull towards the center. So this is the density profile, which is very important. So this is a problem because we don't really know what to use. And at some point, it becomes really expensive, right? We have the turbulence. We don't know the perturbation scale. We need random seeds. We need to choose different density profiles. And so now we are easily at 100 simulations we need to do. And then for one core mass, right? And so in order to get some statistical sampling, this becomes, an expensive problem. Okay. So yeah, and then it's not surprising actually that centrally condensed cores lead to relatively high mass stars, because you collapse everything to the center. Right, and turbulence we already talked about. And so this is then just a few disks, like a gallery of disks, which I wanted to show you, again, depending on the initial perturbation scale. So for large perturbations, high angular momentum, you get very nice large disks. But for these smaller scale perturbations, you get fragmentation, and you also get just tiny disks because there's very little angular momentum in the cores. But however, we know that core disks actually exist. It's also interesting to look at their rotational profiles. So you can look at the angular velocity profiles. For a Keplerian disk, you would expect that the rotational velocity goes with r to the -1/2. Actually, and this has also been found in some disks, in particular around high mass stars. So here, for example, papers by Ginsburg and Moscadelli. These were, I think, 15 and 10 solar mass central stars. For disks which are relatively massive, so either early stage or lower mass objects, we actually find that the rotational profiles can be different from Keplerian. So you can have flatter rotation profiles, for example, and here also magnetic fields are very important. Maybe you heard about the magnetic braking catastrophe, meaning that with ideal MHD, it is actually angular momentum transport becomes so efficient due to magnetic braking that disks are like very small and not in agreement with observations, and that's why you need to have non-ideal MHD. So I would just point you here to this review by Bo Zhao, which I found quite nice. Okay, so now a little bit about stellar feedback, because we've talked now about how we collapse the core into stars, but now the stars also start to radiate and affect the core. And we want to understand how we would actually get the IMF. We said the peak of the IMF is not set by the opacity limit itself, but it's higher than that. So there must be something setting the peak of the IMF. So what is it? So we have several sources of feedback. The one we always have, no matter whether we have high or low mass stars, is protostellar jets and outflows. And in particular for low mass stars, they can be very important, as you will see in a minute. Then we also have stellar winds, which are only active for massive stars, because low mass stars don't produce stellar winds. They have a different structure. Then we have radiative feedback, and here we have to distinguish between non-ionizing radiation, which comes from all stars, and ionizing radiation, which mostly comes from massive stars. Because ionizing radiation affects the gas, similar to X-rays. And so therefore also the radiation transport needs to be treated in a slightly different way. And then of course we have supernovae, but for our purpose, I think we can neglect those, because even the most massive stars have lifetimes of 3 million years or longer, meaning that, you know, the core collapse, which takes several 100,000 years, maybe is already long gone by the time supernova explode. However, not all the cores in a cloud start collapsing at the same time, of course. So supernovae from other regions could affect star-forming cores somewhere else. So this is, but I think Melanie will talk more about this. She told me. Okay, so let's look a little bit about protostellar outflows. So this is a model we did where we had a 1 solar mass core, 1 AU resolution, and you can see how the core is shaped by the protostellar outflow. I think you saw it. I have no time to show it again. And so what you need to do here in order, so you have two possibilities. Either you model the outflow self-consistently, but then you need to have magnetic simulations, so MHD for sure. And you need to have super high resolution, because the outflows are launched from the region where the protostar accretes. And if you do not resolve at least 1 AU or smaller, then you don't get them at all. And it actually, the velocities you get depend on your resolution. So the higher you go, then you at some point you will start to get the jet component, which is very fast. And if you have lower resolution, you only get your wider angle wind. So this is not good, right? Because it's highly resolution dependent, and your models are very sensitive to that. And so what we did instead was that we chose a subgrid model. So basically our sink mass, we split up into a stellar mass and a mass of an inner accretion disk, so IAD, and similarly the luminosity. And so then you need a model which describes how you accrete from the inner accretion disk onto the star. So this is this stellar accretion rate. And it has two components, namely, there can be like a background accretion, which is like a low, steady accretion rate. And then there can be an accretion rate because this model is based on MRI instability in the inner disk, so magnetorotational instability. There can be an accretion rate which basically is only active when you get a flush of accretion onto the center. And so if we do that, then we get episodic accretion, which is in agreement with observations, and which can reduce your star formation efficiency by about a factor of 2 in the cores. And you can also look at how much gas is pushed out and so on. And I showed you this in detail because I will skip this HIMA star stuff. If you're interested, let me know. I showed you this in detail because it seems to be the case that protostellar outflows and jets are very important for setting the peak of the IMF. And it must be some feedback from a low mass star, because the peak of the IMF is for low mass stars, right? so it can't be high mass feedback, which is setting the peak of the IMF. It must be low mass star feedback. And so it basically can only be either radiative heating or it can be jets and outflows. And so I think it's still not completely conclusive what it is. So there you can basically do you can basically set the peak of the IMF with these processes. And there's this nice work by the Starforge project, for example, where they look at 500 solar mass cloud, I think, which is collapsing and forming stars with high resolution. This is with GISM2, so it's basically modified SPH. They see that protostellar jets are very important for setting the peak of the IMF, but they point out that there's still quite a large variation in the IMF properties. And so they say that probably additional physics is needed. And I suppose that this will be the radiative heating, which has been found by Krumholz to be quite effective in this regard. All right. So this is just showing the simulation again as a time evolution. This is the Starforge simulation. Okay, and maybe just one word about star formation efficiency, because we've talked about how efficient is star formation. So for these molecular clouds, which have around 10,000 solar masses or so, here 20,000 solar masses, you can disperse them by ionizing radiation. So ionizing radiation is most effective for this. Also, when you look at massive star-forming regions, ionizing radiation is the dominant feedback mechanism. However, if you go to very dense structures, let me just skip this. When you go to very dense clouds, so here's the star formation efficiency as a function of cloud surface density. So the denser you go, the higher star formation efficiency you get. And this is work by Kim, but then there's also Grudich and Howard and so on. They all find the same thing. So more denser clouds, more star formation efficiency. And for our individual cores, this is not such a big problem. But for whole clouds, this is a problem because overall, most stars form in massive clouds. And we want to have low efficiency overall on the large scales. And so I think this is still something we need to figure out. We need to figure out how much feedback comes from the small scales where we form the stars inside the cores out to the larger scales. Because these models, they start at slightly larger scales. So they resolve maybe 0.05 parsec or something like this, maybe a little bit smaller. But this is basically the whole core, right? So we need to couple what's happening on the smallest scales where stars actually form and what's happening on the larger scales in the future. I think this is one of the big things we need to do. And so this is why I want to raise this here also as an open question. So how does the CMF map into the IMF? So it seems that you could have the CMF mapping onto the IMF, then you would have some star formation efficiency in cores. You get a one-to-one mapping, basically. The other model, as we just talked about, you could have them not being really related, but there's dynamical interaction and stochastic accretion. And this is still not solved, and we need high-resolution simulations to look into this. And so this brings me to my conclusions and open questions. So for fragmentation, we saw that it depends on many parameters: density profile, magnetic field strength, virial parameter, and whatnot. And we still need to better constrain these parameters in order to actually understand how cores fragment. And so I think we need to understand whether cores are real objects or whether they're just fluctuations, and how much they are interacting with the environment, how much mass do they accrete while they are forming stars. And to model star formation, I think we need to improve beyond the state of the art in terms of modeling larger scale cloud environment at the same time as the star formation process itself, but this will definitely be a supercomputing challenge. And we also have to think about whether we are missing more physics. Yeah, and for the IMF and star formation efficiency, we then can figure out whether the CMF maps into the IMF or not, and also what is the star formation efficiency in cores, and how does the feedback from the cores affect the larger scale environment and on what time scale. So for now, we are plugging this in as immediate feedback on the larger scale models, but whether this is actually true is not resolved. All right. So yeah, thank you very much for listening, and I'm happy to take questions. Mm-hmm. All right. Thank you.
So any questions? We still have 10 minutes for questions.
So about your statement on triple systems.
On what, sorry?
Triple systems
Yes.
you showed. So as you said, the in-body simulations, triples are not so stable. I thought including hydro and disk, you maybe stabilize the system, but you said the system is also unstable. So can you comment on further?
Yeah, I think for this, we would need to do more of a statistical study, and this hasn't been really done, I think, because the, yeah, I mean, we need to simulate hundreds and thousands of these objects in order to actually say something about stability. And yeah, I think to my knowledge, this hasn't been done. N-body simulations have been done, right? With large statistical sampling, and this is great, but not with star formation and disk evolution. Yeah.
But also the in-body results depend on how they can integrate at very close. Are you simulate you think particle? Are you simulating in-body part as accurate as in-body case?
Not in the simulation I showed you. Right now we have in the code a fourth order integration scheme, but we don't. I mean, that's quite great. That's quite good. But I mean, when you have very tight binaries, of course, the time step kills you. So then you need to get to these chain algorithms or something like this, which at the moment we don't have in our grid code. But there's this torch framework, which is based on Amuse. For example, Mordecai is working with this, Mordecai McLeod, and also Claude Cormier. Sorry, I cannot pronounce hers. She has a double last name, and she has a very nice paper out. And they are using an n-body integrator, I think Petra or something, together with Flash. Yeah.
Okay.
So to get binaries.
Any questions from the students?
Yeah, so thanks for the great lecture. I want to ask you what do you think about the Lee and Hannibal theory about the peak of the IMF being, if you resolve the adiabatic end of the high density, so the first adiabatic core, the high density regime, then you get the peak of the IMF. So has anybody tried that and feedback yet?
It's a good question. I don't know. I would need to check.
Yeah.
Yeah.
That would be a nice direction to take. Yeah.
I don't know. Need to check it. Because right now I don't know what they did in this Pelkonen paper. But I think they didn't. I mean, that's basically isothermal stuff. So I don't think this is appropriate. Yeah, and the other ones don't include the other part. Yeah. All right.
Questions from students in less than their 27 years of PhD? Yes.
Hello, thank you for the nice talk. So my question is, when you are plotting the IMF, suppose you have the IMF at some particular time. Now, after some time passes, the stars will accrete some mass and the IMF should change, right? So do you expect this to change by a large amount as time goes on?
So the IMF, which I showed you, is basically the IMF for stars at the main sequence, so the final one, right? So basically your question, if I understand correctly, is how how does the protostellar IMF look
Mhm.
like, and how does this evolve into the IMF as we know it?
Yeah.
Yeah, so this is exactly what we need to understand, because for that, I mean, we know that accretion plays a role, right? So all the stars are accreting. Yeah, so basically we need to know what is the mass of like the seed fragments, how much is coming through disk accretion, how much is coming through core accretion, and so on. So this is exactly the tricky question, basically, which needs to be solved. Yeah.
Okay, thank you.
But if you if you follow the idea that you get the IMF from the CMF, then there's not so much flexibility. If you think that there's only like a statistical mapping, then there's much more flexibility in the individual objects, right? Yeah. And yeah. All right, let's leave it at that.
I was wondering if there is like in a galaxy a radial dependence on the scale of turbulence, such that you can make guesses about the properties of the star formation regions dependent on the radius.
So that's a very good question. So I think in general, the velocity dispersion should be a little bit higher when you go towards the center of the galaxy. But then it depends on where exactly you are, because it seems that like in bars, you have regions of high turbulence, for example, or yeah, then while you are more quiescent when you're further out. But this question relates to the question how turbulence is actually driven in molecular clouds, and this is unsolved at the moment, because there's a competition between driving of turbulence by galactic effects, like galactic dynamical instabilities in the galaxy, spiral arms, bars, etc. There's also inflow onto the galaxy, right? Feedback, on the other hand, can also drive turbulence. And so I think right now it's not really clear how the two, how important they are with respect to each other. So they're like competing models. And so you could get high turbulence either due to, very perturbed galactic dynamics, but you could also get high turbulence because you have a little starburst and feedback is pushing a lot. And then you locally get a very highly turbulent environment. But this needs definitely further research. And I'm not really aware of that there's like a solid gradient, in velocity dispersion, but maybe someone else can comment on this. Okay. It's also, I mean, like if you go to the galactic center, you're on average warmer, so your sound speed is a little higher. So question is then, are you really, I mean, the question is if you're more supersonic. I don't think you are. I mean, you would anyway dissipate. No.
I have a question about the way dust is treated in this simulation. Is it a separate component, or is it completely coupled to the gas phase?
So that's a very good question. It's different in every simulation. So in our latest simulation, and also in Matthew Bates, there are at least two temperatures. So there's a dust temperature and a gas temperature. And the two are not the same. I skipped this before, but maybe I can show you now. Yeah, sorry, it's a bit small, but basically here you have the dust temperature, and this is the gas temperature, and this is radiation temperature on the x-axis. And so basically you see that dust and gas temperature are different because you can have heating by accretion shocks, and on the other hand, the dust in very dense regions can be heated by radiation, and then it is taking some time to heat the gas. So they are not necessarily the same, in particular in these prestellar cores. Then I think people are working on doing better implementations of dust. I mean, like also taking into account an evolving size distribution. But I'm not really aware of anything in like collapse simulations. I know that people have implemented these things and done simulations in disks. where of course this is also very important to look at the growth of dust and settling of dust and so on. Yes, but this is something to look into in the future as well. I agree.
What about the effect of the long-term history of the gas? You have GISM2, so they are not completely destroyed by star and can reform later on. And so the chemistry can stay on. So does that have an effect on the star formation history?
I think it does, because so what we generally see is that so for molecular hydrogen, when you start with no molecular hydrogen, then you need the dust to shield the gas in order to form the molecular hydrogen. But once you have molecular hydrogen, self-shielding is very important. And so if you don't destroy all of the molecules, similar for CO, you have shielding of CO by dust, by H2, and by CO itself. And so if you already have molecules, then I think it's easier to form more of them again. So I think it will. But then the question is, how much does the star formation depend on the molecular gas fraction? I mean, that's another issue. But I think it's easier to form molecules if you already have some around. Yeah.
Okay, we should stop here. So let's thank Steffi again.
Yeah, thank you.